Hello, I'm Seema and welcome to part 26 of the chapter States of Matter. We have been discussing the physical properties of liquids. In the previous video, I told you about vapor pressure, and now in this video, I'm going to tell you about surface tension. But before I come to the actual discussion of the topic or the property of surface tension, I have prepared a little demonstration for you. I would like you to see that first, and then I'll move on to explaining what surface tension is. So give me a minute. Let me just adjust this so that I can show you what I have prepared for you. Now I have a bunch of material here, and I intend to tell you about or draw your attention to some of the things that you have already observed in life. I have a bunch of coins in my hand, and if you see, they can easily fall off. They're not sticking to each other, right? A bunch of coins, if you take them and you just try to slip them through from one palm to the other, they easily fall off. But if I have the same bunch of coins and they are wetted in water, what happens to the coins when they are wetted in water? Let me just see. Now this bunch of coins are wetted in water, and if you really see, they do not slip as easily as those. They kind of stick together and the falling off is not as easy. If you took a little sand, let us say, now this bunch of coins, I'll leave it here. I'll have to dry it my hands. I have sand here. Do you see sand? It's dry and it's moving. It's moving because the sand particles are not sticking to each other, right? The sand, I'll just dry my hands a little. If I try to pour the sand over something, it pours easily. Do you see? The sand is falling off easily because the molecules, or rather the particles of sand, they're not sticking to each other. On the other hand, if I wet the sand, what do I observe? When I wet it, I observe the sand is now sticking. Do you see this? It's now sticking and it does not fall off. It cannot flow as it did. Some of it has, like it has gone wet, and now in order to move it, I really have to use force, and it does not fall off easily. Can you see the sand? It does not fall off as it did freely as the dry sand did. So there is some force which is holding these molecules of water, or rather there is so much of attraction between the molecules of water that they bind the things that they are stuck to. The water molecules, when they are stuck to some other particles like the coins, or in this case the sand, they tend to stick those particles together also. It's not the particles of sand were not attracting themselves. So they could be poured easily. The dry coins could move easily. So the sand and the coins, they could move easily, but the wet sand, it got stuck. Give me a moment and I'll just wash my hands and I'll show you a few more things. Another thing. Have you ever noticed that if you put a straw into a drink that you're drinking, the straw may be thick, it may be thinner, or it may be really very thin, right? You all use straws to drink. So, have you ever noticed, if you are a little careful when you are watching your drink and the straw as you put it in it, you will notice that the level of the liquid or the drink that you're drinking is not the same in the jar or in the glass. It's a little different in the straw. So what is it? What is it that is causing? You will find that if the straw is thicker and it's water, the water does not rise much. But if the straw is thinner, it appears as if the level of the water is higher in the straw than it is in the glass. So what is causing this rise of water in a straw? If I put the same straw in liquid mercury, mercury is a dense metal and it's a liquid. So if I put the straw in mercury, I will find that the level of mercury in the straw would actually be lower than what it is in the container that I'm holding mercury in. And if you ever played with mercury as kids, sometimes the thermometer would break and as kids we would play with the mercury. It forms small balls, spherical balls. And these balls, if you could actually, it moves, mercury moves in the form of those balls. Because the attraction between the molecules of mercury is so strong that it just keeps it strongly held together. And that shape in which the force would be minimum, or that shape in which the molecules could be closest, would be the spherical shape. That's why you find mercury or liquids turning into spheres. You must have noticed raindrops coming down. They appear to be elliptical. They are elliptical. They don't just appear to be elliptical. They are elliptical because they are falling off from the sky, and they were supposed to be spherical because of this force of attraction, but due to gravity, the lower part seems to be coming faster and therefore it appears to be elliptical. But if we did not have gravity and we looked at raindrops where there was no gravity, raindrops would also be spherical in shape. This rising of liquids in straws or small thin tubes, they are called, such thin tubes or even thinner tubes are known as capillaries. And this action of the liquid rising or falling in the capillary is known as capillary action. And I'll just show you a few more examples of capillary action. This is an oil lamp. The oil lamp is often used for prayers or to light up a little room. And this is a cotton thread, right? I've just made so this is the cotton thread that I've made for the oil lamp. Now, if I just insert this into the oil, what will I observe? I'll observe that the oil starts rising in the cotton. What is happening here is that the cotton you know how cotton is, it's fibrous. I've just put the fibers together. So when they come together, all those gaps in between, they start acting as capillaries. And when they start acting as capillaries, when you insert the cotton into the oil, we find that it starts rising in this thread. So let me just put it inside, and I will let it stay here where it stands and leave a little bit of it out for you to see what happens to the oil in a little while. We all use pens. What happens in a pen? The pen, if you see, has a refill in it, a ballpoint pen, and the refill is thin. It's the same capillary action which is taking place. The ink moves in the refill due to the capillary action. Why do we see this capillary action? Because the molecules of the liquid, they have a strong attraction between themselves. And it is this strong attraction which is responsible for all the capillary action. It is this strong attraction which is responsible for binding things which would not otherwise be bound together. Here I got some soy sauce in a container. Now I'll take a little tissue and I'm going to dip a corner of the tissue in the soy sauce. And what do I observe? You would have done this a number of times when you have a colored liquid and you dip the tissue into it. You would observe that the liquid, it starts rising, it starts wetting the tissue. I just dipped a little bit of it, just the tip I dipped into it. But I find that now the liquid has risen to a much higher level. So this is also due to capillary action, and all of this can be explained on the basis of this one property that I'm going to tell you about today, that is surface tension. Now I'll just bring the camera closer for you to see all of these things so that then I can go back to my class. Bear with me for a moment. Okay, now I want you to focus on this lamp. I told you that I put the wick into the lamp, the cotton thread that I made, and if you notice, the oil has risen. It has risen and the entire wick has turned yellow. Do you notice this? What I took was just white cotton. And the white cotton you can see now, do you see it? It's yellow. Similarly, the soy sauce that I took, I'm now going to dip the tissue again in the soy sauce. Just the tip. And do you see it rising? Do you see how it rises? This is also due to capillary action. Then, the liquid, the different straws that are present, we find that the level of water inside the straws, I don't know if you can observe it like this. The level of water inside the straws is different from the level that it actually is. Unfortunately, I can't show it nicely to you here. The thinner the straw, the more would be the rise or the dip. Then come the sand. Do you see the dry sand? The particles are free. They are not stuck. But I have wet sand here, and wet sand cannot be moved. Coins, when they are dry, they are easy to move. But coins that are wet, they would tend to stick to each other. And it will not be so easy to move them. Their movement would not be as easy. So these were a few examples where we can see that there is a great attraction between the molecules of liquids. Let us now come to our topic, that is surface tension. So now that you have seen a few demonstrations, let us refocus and come back to our topic. I told you that mercury, if you have seen, is spherical. Drops of mercury are spherical in shape. And these spherical drops are because of the strong attraction between the atoms of mercury. The wet particles of soil we saw, they stuck together. They stuck together not because the soil particles were attracting each other, because the dry particles were separated. They were easy to pour. But on the other hand, the wet particles, they stuck together. The reason was the attraction between the molecules of water which were holding the sand particles together. I told you about capillary tubes and capillary action. When you have a thin tube and you dip it in a liquid, depending on the density of the liquid either rises in the capillary or it goes down in the capillary in comparison to the level of the liquid in the jar in which you dipped it. So this action is known as capillary action. For example, if you had mercury, in the case of mercury, we would find mercury is a dense liquid. So if you put a glass capillary into mercury, we would find that the level would dip. Inside the capillary, the level would dip. Why? Because it's a dense liquid, the force of attraction is much stronger, and therefore that force of attraction does not let the mercury rise easily in the capillary. On the other hand, if the liquid is less dense and the force of attraction is not so strong, then the glass of the capillary tube, the liquid like water would get attracted to the glass of the liquid also, of the capillary tube also, and the liquid will start rising in the capillary tube. The thinner the tube, higher would be the rise or the fall of the liquid. So one such example is, what do we do? We have a plant here. What do we do when we grow plants? Where do we put the water? When we are watering plants, what do? We water the pot. We water the soil. When we water the soil, what happens? How does the water reach the tips of the plant? How does it reach the flowers? Because the plants, they have tissue which is known as xylem, and this tissue is like like we have veins in our body, like we have arteries and veins. They are thin capillaries, and although you are pouring water into the pot or you're giving water in the soil, it is this capillary action which causes the water to rise up to the tip of the plant. You can imagine you have trees which are so many feet high. How does the water reach the tip of the tree when you're only watering the soil? The reason for it is capillary action. Why does this happen? Why do we observe these things? Why did the oil rise in the wick of the lamp? It rose because of capillary action. Why did the tissue get wet, or why did it start absorbing the liquid so easily? The soy sauce that I used. It was again capillary action. The attraction between the molecules of the liquid is so strong that they do not just leave the molecules. When one molecule starts moving away, the others, they start going along with it. So what do we find? If we took a jar and a beaker and we had water in it, what are the forces that would be acting on the molecules of water? A water molecule which is in the bulk of the liquid, that is somewhere in the middle of the jar, we would find that it is being attracted equally by all other molecules of water around it. So the net force of attraction that it experiences in the bulk, in the middle, is zero because it's being pulled equally by all the molecules all around it. But if a molecule of water is on the tip or on the surface, then there is no water molecule above it which is pulling it up. Rather, there are water molecules beside it and under it which are pulling it downwards. As a result of this, what happens? The molecules on the surface, they tend to be pulled towards the inside of the liquid, the bulk of the liquid. If this inside, now we have a beaker and we know liquids take the shape of the container that you put it in. If it was a little amount of water, then if the outer surface molecules would have been attracted to the center, then what shape would it have acquired? It would have acquired the spherical shape. So a drop of water should be spherical in shape. But we find drops of water to be elliptical because of gravity. When gravity pulls a drop of water, it comes down in the form, it becomes elliptical. It's gravity which is causing it. If there was no gravity, it would be spherical in shape. Why? Because the molecules which are present on the surface of a liquid, they tend to be attracted only by the center. They are being attracted towards the inside. So if you imagine the surface to be a line on top, a straight line, then this energy is pulling it perpendicularly downwards. This energy is perpendicular to the surface. If the surface was a line, then this force which is pulling, or the attraction, is in the downward direction. It is perpendicular to it. This force that attracts the molecules at the surface towards the center of the bulk of the liquid is known as surface tension. Why is it called surface tension? Have you ever touched the surface of water? If you touch it, you find it feels like a balloon. Just before you really wet your hand, if you just touch it lightly on the surface, very lightly, you'll find that it moves as if it's a balloon. The entire membrane seems to be stretched out. It is like a balloon which is, it is as if it has walls. If you put a twig over it, which is less dense, we find it starts floating over the water. That is because the force of attraction, the molecules of water are holding themselves so strongly together, and this force is actually pulling the molecules at the surface towards the center, so it acts perpendicularly to the surface of the liquid, and this force is known as surface tension. Liquids tend to minimize their surface area. I just told you, if this force is acting towards the center, what would be the shape in which there would be least tension in the case of molecules on the surface? The shape would be spherical, because a spherical shape is the smallest shape that can be acquired. So the molecules would, or the liquid would, try to acquire a spherical shape in order to have minimum tension on the surface. So, and that is why mercury, which has very strong surface tension and it is a dense liquid, if you take small droplets of mercury, they are absolutely spherical. So they have a minimum, and by acquiring this spherical shape, they have the minimum number of molecules on the surface. If you want to stretch the surface of a liquid, if you take a liquid and you start pulling, you want to stretch it, you want to spread it out, you will have to use energy against this attraction. If you want to spread out a liquid, you need to use energy against this force of attraction. So to stretch out the surface, you will have to work against this force of attraction. So this would require energy, and this energy which is required to increase the surface of a liquid by 1 unit is known as surface energy. And what would the unit of this energy be? It would be joules per meter square. If we want to increase the surface area by 1 meter square, then the number of joules required to increase the surface area of the liquid by 1 meter square would be is known as the surface energy, and the energy required would be in joules. The number of joules required to increase the surface area of the liquid by 1 meter square, that would be its surface energy. So let us see what is surface tension once again. Surface tension is defined as the force acting per unit length perpendicular to the line drawn on the surface of the liquid. If I drew a line on the surface of the liquid, the energy perpendicular to this would be surface tension. It is represented by a Greek letter gamma. And what would be the dimensions of this of surface tension? If you measured it, what would be its dimensions? It would be how many kgs per second square, or if you are taking the SI units, then it would be reported in newtons per meter, because surface tension, it would have the unit of force, because it is a force which is acting downwards for the molecules on the surface. So when would the liquid acquire the lowest energy state? Obviously when it has a shape where it has minimum tension, and that shape is spherical. I already explained it to you. And that's why mercury drops are spherical and raindrops are elliptical. There's one application of surface tension which you should know of, which is very interesting. Have you observed, I just used this glass table, or let's get this glass. Glass has very sharp edges, but when this glass is made and I touch the edges, they are not sharp, they are rounded, they do not cut my hand. If glass breaks and it has sharp edges, and if you touch it, you tend to injure yourself. But the glass material or glass articles that we use every day, they seem to have rounded edges. How does glass have these rounded edges? The knowledge of surface tension is used to round off the edges of glass. How is it done? The glass is made into whatever shape it is, and when it is a liquid, the edges, they are heated. And when they are heated, glass melts very easily. So when the edges are heated, the glass, it melts, and when it melts, what shape would it acquire due to surface tension? Spherical. So the edges which were sharp, they would tend to become rounded. And when they become rounded, the sharpness of the edges is lost and it becomes nice and round, and that is called, this process is known as the fire polishing of glass. So this is called fire polishing of glass. So these are just the examples that I showed you, capillary action, and then I showed you that sand, when it's inside water, when it is inside the water and you're moving it, a little bit of it, it would very easily move, See, if I have sand in this glass, and I just move it with a straw, the particles are freely moving. But when I took them out and I had wet sand, it remained stuck together. So this shows that sand, it sticks when it is wet. All of this can be explained on the basis of surface tension. Does surface tension depend on temperature? Yes, it does. Because as the temperature increases, the energy of the molecules would increase. And if energy of the molecules would increase, they would tend to move away from each other. So the molecules which are on the surface, they have more energy, they would have a greater tendency to move away, and therefore surface tension, which is the force which is holding them down, would be lower. So surface tension increases with decrease of temperature, or it decreases with increase of temperature. So this was surface tension. If you found the video helpful, please give it a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.